All right, so we're going to start off by doing this question over here, which is going to be our pipeline question, right? So we know it's going to be a 5-stage pipeline. And we also know because of that, right, we want everyone to have every instruction to have exactly 5 states. So even if we end up having something along the lines of, let's say something like a branch in which we don't have the full 5 instruction cycles that we're going to be going through, we add what's called no ops in order to kind of still manage to go through that. So that's the first step, right? We know that it's going to be 5-stage pipeline, of course. And we also know that there's going to be full data forwarding involved. So that means that if we have an R-type instruction, we can essentially do what's called data forwarding. And what data forwarding lets us do is it kind of lets us skip a cycle. And instead of waiting for the write back to happen, we can do what's called forwarding our data that's being done in that R-type instruction and finish our calculation and immediately use it in the next cycle. So this is great because otherwise, if we did not have data forwarding, we'd have to use stalling. So we want to try to avoid that as much as possible, right? And we also have the branch predictor here as well. We know that this is going to be dynamic 2-bit weakly not taken. So with branch predictors, right, there's a couple of different ways that we can deal with them. So a branch predictor essentially tells us during the decode stage, which is when we adjust our program counter, right, to the next instruction that we have to go to, is do I take the branch or do I not take the branch, right? Because until I get to decode, I don't realize if it's a branch instruction or not. So I can either, with no branch predictor, have to just take the next instruction and hope for the best, or if it's a branch predictor that says to take the branch, then take the branch and hope that I made the right decision. So branch predictors aren't always right. And we try to minimize that by having a couple of different versions. So there is static branch predictors. They stay the same for the entire execution of the program. So if it's taken, that means every single branch that you do, you're going to take the branch. With not taken, it's going to be a little bit different, right? You're not going to take the branch. There's also dynamic 1-bit and 2-bit. Dynamic 1-bit switches every time that you're essentially, let's say, wrong. If you have like a starting point as a taken branch predictor and go to an actual not taken branch, that's telling you that there's going to be a problem between that. And that's going to tell you the next time, switch to what it was supposed to be, not taken. So I like to think of it as, let's say you're playing a game and flipping a coin, right? If you get heads and like it's you say heads and it actually is heads, then you win. So you'd be more inclined to keep your strategy, so to speak, of staying with heads. But if you said heads and the actual answer was tails, then maybe you would switch your answer to tails because that was what the actual answer was. So it's really switching to whatever the value turns out to be. So if you were correct in predicting it, which again, kind of 50-50 chance, then you can just keep it. If not, then you would have to just switch it to the opposite value. The last type, which is what we're using in this case, is dynamic 2-bit weakly not taken in this case. So with dynamic 2-bit, we have more than just 2 states. We have 4 states. And the way that we like to define this is we start out with strongly taken, we have weakly taken, we have weakly not taken, and we have strongly not taken. So when we have strongly taken or weakly taken, these are essentially our taken stages, right? Like the last time they tell us, okay, if you're stuck with the branch, take it, take the branch. The weakly not taken and strongly not taken are telling you, don't take the branch. So that's really what we're aiming for here. And you can also think of these as an automata, right? It's going back a little bit to 320 if you've taken it already, but you could think of it as like a state diagram. So anytime that I'm in a strongly taken state, right, I can't go up the ranking anymore, let's say. So any takens are going to keep me in that taken stage. But if I go from strongly taken and I have one not taken, that's going to bring me down the ranking a little bit. And another one would bring me down another ranking, and another one. Once I'm in strongly not taken, any more not takens would just be a loop around there. Likewise, if I go from strongly not taken and get myself a taken, that brings me up a level, and another level, and another level. So that's kind of how we are dealing with this. So in this case, right, we are starting out with weakly not taken. That's this stage over here. And we just want to keep that in mind because this is where we're going to be starting. And whatever the outcome of our branch is going to be is going to either push us upwards or downwards. All right, now we're good to start the question. So we know that we have a bunch of instructions over here. And because this is probably something you've seen before, because we have done the non-pipeline version of this before in class, I'm going to kind of skip a little bit ahead and just kind of go over the main parts of this code that are going to be important for this. So we know that essentially we're dealing with a branch here, right? We know this because we have the exam3 label here, and we have a branch, if not equal, to the exam3 label. So this is telling us, hey, if I branch, if this and this are not equal, right? If this is not equal to 0, I am going to branch myself to instruction 4. So that's kind of what we're dealing with over here. Now, we know also that what just happened? Okay, that's fine. So we know that as well that if we have over here in instruction 9, every time we run this code, we're subtracting 1 from T1. Well, what was T1 to start with? 600. So every time we do this loop, we're going to start at 600 and in decrement go down by 1. So we're going to start at 600, then 599, 598, etc., until what point? Branch on not equal to 0. We will continue branching until we do equal 0. So because of that, right, we know that this is going to run 600 times. So it's going to keep going and going and going and going until we finally get to 0. At that point, then we're going to stop. So with that being said, right, we know that we're going to have a lot of loops here. But we also know that our dynamic 2-bit branch predictor tells us to start at weakly not taken, meaning it's going to tell us don't take that branch. Well, that's going to be causing a little bit of a problem because we're supposed to take the branch, right? We know as humans reading this that we're supposed to take the branch, but the computer going bit by bit, line by line, isn't going to know that. So that's what we're going to think about as we do the pipelining for this. Okay, the pipelining itself is pretty simple, right? So we can't write out all 600 instructions, like obviously, but we're going to kind of just show a little bit of what's going on. The way I like to do this is to show the first loop of the loop, right? And like the end of it as well. So that's kind of like the end behavior of the loop as well. So let's walk through this. We start out with instruction 1, and instruction 1 is a load word, right? So we're going to start out fetch decode, oops. We're going to do fetch decode exec mem and write back. Okay. And the next one, right, we have a load immediate. So load immediate, even though it says load, this kind of functions very similar to an R type because we don't go into memory at all. This is saying load an immediate value. Don't just go into a place in your memory, so to speak. So it's loading in the value 600. So because of that, I'm going to be doing fetch decode exec instead of memory. I'm not going into mem, but I need to have 5 stages because the question tells me, hey, it's 5 stages. So now I'm going to do what's called no ops and write back. Please stop moving the screen. Thank you. Not sure if I can um, change the permissions on this. Kevin, I don't know if you can change the permissions on the whiteboard or not.
Oh, are people moving the screen?
Yeah.
Sorry. Let me see if I can do it.
Yeah, just if people could just not. Okay.
Oh, well, I didn't.
Okay. All right. Anyway, so now we have instruction 3, right? And what that is doing is, one second. Okay, instruction 3 over here is going to be starting over here. Under that point, please stop moving the screen. If I need to, I'm going to go on um, a different program, but we really need the whiteboard not to move, please.
I think I managed to this thing remove. This is collaborate with Zoom apps. I can
Okay, perfect.
remove that now. Yeah, you can try that.
Gotcha. All right.
And select the hand, make it gray, so that will make it move around.
All right, so now we have ourselves in instruction 3. This is also another load immediate, so we have fetch, decode. What the heck just happened? Just disappeared. Okay, that is not working then. All right, you know what? Let me just go onto the sketchpad I usually use for this. Okay, yeah, sorry. I'm just having a bit of technical issues because like my iPad is not really connecting right now. So,
Or another question. So, are you able to use the whiteboard again? Because I maybe might have done something on accident. Try opening it up again.
um, oh, wait, I think I got it.
Okay.
All right, perfect.
Sorry, I moved it on accident. There we go. But
Yeah, that's all right.
that's good.
Okay, yeah. All right, so we're good now. All right, so now we have instruction 3 is saying another load immediate. So we have ourselves fetch, decode, exec, no ops, and then write back. Okay. And that is going to be, okay, wait, now this is not working on my end. Okay, that's not good. Okay, that's really great. My iPad is not even working at all. All right, well, I'll just have to use my computer then. All right, so now we have instruction 4, right? This is where our loop begins. So this is saying now load word, all right? This is going to be another load word. So we're going to start out fetching over here, decoding. But whenever I go through decode, I want to also check for dependencies because decode also decodes the dependencies. This is going to tell me if any of the arguments are being used somewhere else within this program. And this is the case because we have T2 over here, right? We need to know the value of T2 before we go into any further. But the problem is, right, we don't know what T2 is until we finish instruction 3. And that's usually over here in the write back stage. But the good part is remember when I said load immediate functions very similar to an R-type instruction? That being similar to an R-type instruction means that I can use data forwarding. Because essentially by the exec stage over here, I'm finished with the value. I don't have to go any further or worry about anything. I can do data forwarding and essentially forward it over here. So this allows me to take the value, that immediate value, that's 0 in this case, which has been finished loading in the exec, and use it in the exec of the next instruction, which is where it's needed. This essentially saves me a cycle because I don't have to stall in this position over here. And I can just continue as I go along. Fetch decode exec. This is a load, so we will do mem and write back. So that's how we're dealing with these data hazards. All right, that's going to be 4. Now for 5, we had add T2 and T3 and put the result in T8. Well, okay, if we start out with fetch and decode data dependencies. Are there data dependencies? Yes. T2 and T3, right? Well, T2 would be up here. So T2 doesn't have a problem anymore because it's already in this write back stage during this cycle, so I don't have to worry about it anymore. I do need to worry about T3. And the problem is T3 comes from instruction 4, but instruction 4 is a load word, not an R type and not a load immediate. Therefore, I cannot data forward. If I cannot data forward, this tells me I have no other choice but to stall. And the problem with stalling is that it stalls the entire pipeline. So unlike like a no ops stage, which just literally is no operation, I have to quite literally stall for every other instruction that is going to happen within this cycle. So you could imagine a list of S coming down this column. Now I can resume after I get to this W point. Once I'm under this W, I can have my E. I always say you can go on the we. Think like you're saying we on a roller coaster. So that's the way that I usually like to think of that. Now that I'm able to exec this guy, right? We know this is an R type because it's an add instruction. Therefore, fetch decode exec, no ops, and write back. So this kind of pushed us down a cycle. You know, that's kind of why we want to avoid stalls as much as possible, but we get it. You know, you can't exactly, you know, avoid them entirely. So the data forwarding is good in some cases. Whenever you can do it, you want to do it. But it's not always possible. So next to keep in mind is we have ourselves instruction number 6, right? That's going to be our next case over here. So instruction number 6 is going to be an add immediate, another R type. And this time we are loading T2 and 2, adding them together, putting them into T6. Well, T2 has been done for some time, so once we fetch, right, and we have to stall in this position, so I cannot decode in this cycle over here. That's why I put the stalls in before I even went further. I have to decode over here. So I decode, I don't see any data dependencies, and it looks good. So I can continue. This is once again an R type, so fetch decode exec, no ops, and write back. All right, now we're in instruction 7. This is going to store word T4 into the memory address held by T2. So we know that T4 has not been used here, and T2 is done much earlier on. So we don't have to worry about data dependencies there. Now, we can't fetch in the usual spot because, again, we have ourselves a stall over here. So I have to fetch one cycle later. I will fetch decode exec mem, and since we don't do write back in stores, I just do no ops at the end. So that is how we're going to handle that stall. Now, at this point, we're pretty good, right? You know, we don't have to worry about this stall anymore at this point. So the next instruction we can fetch normally now at what we would think would be more of the normal cycle. Okay, so that was instruction 7. Now we have 8. So 8 is yet another R-type. Now, this over here is saying multiply T2 and T4 together and put it into T7. I fetch over here. Now, the reason I'm fetching over here and not right next to the stall is because I can't fetch on the same cycle. I have to put it under the decode of the previous one. So otherwise, I'm good to continue to code. Are there any data dependencies? Well, it may look like this guy over here would be a data dependency, but it's actually not. The reason is the parentheses mean an address. And when we have an address, right, this is saying the address in memory, not the register itself. So it's also saying that it's the address in memory represented by whatever is in T2. Now, at this point, I think T2 would have been still 0, right? Because we didn't change it since that point. So this is quite literally just saying what's in memory address 0. That's where we're storing T4 to. Therefore, this is not a data dependency, even though it may look like that. So that's great to know because, we don't have to data forward anything. Okay, so now that we got that done, right, fetch, decode, exec, I'm good to exec. There's no other data dependencies. There's going to be no ops and write back. Awesome. We got ourselves 9 and 10. Almost there. 9 is another R type. This is going to be T1. So we're going to do fetch, decode. I don't see any data dependencies here, right? T1 has not, it's been declared long ago. There's no problems there. So we got ourselves fetch, decode, exec, no ops, because this is an R type, and write back. Okay. And instruction 10, this is where it gets a little fun. We got ourselves a branch. So I'm going to start out with my branch, fetch, decode. Decode, a lot of stuff is happening in branches. It's not just checking data dependencies, which there clearly is a data dependency, but we'll get to that in a moment. But we also need to figure out where are we going to branch to, because also in the decode is where we're going to fetch the next instruction. So we need to figure out, do we take the branch or do we not take the branch? This is going to tell us what our next instruction is going to be. So we know that in this case, there's also a data dependency. So let's handle that before we decide where we're going to go to next. We know this is supposed to be a T, by the way. I know it says an R, but it's T in this case. T and R are both registers, so it's the same thing. But for whatever reason, there's a bit of a mistake there. So this is saying branch on not equal to 0. You compare T1 and the 0 register. Well, the problem is T1's value is not updated until instruction 9 is finished. So that means I need to either stall or data forward if possible. Well, is it possible to data forward? Absolutely. This is an R-type instruction. So I can data forward this E to this E. Fetch, decode, exec, no ops, and write back. This guy is all done. Great. Now, before I go into the branch, which can be a little bit confusing, I'm just going to take a minute and pause. For the first iteration of the loop, does this make sense to everyone? Are there any questions? You could put in the chat or in mute, whatever's best for you.
So Lauren, anytime there's a data dependency from a previous string, then we could full forward then?
The only times you can full forward when that happens is if the instruction you're taking the data from is an R type or load immediate. So you can only do it if it's something like an add or a subtract or a multiply or a load immediate. any of those that have the fetch decode exec no ops write back scheme to it. Basically, if you don't have to go to memory, that's really where it is, because what you're doing is essentially saying, if I can finish by the exec stage and use that data, then you can forward it. Does that make sense?
Yes. Thank you.
Yeah, of course. So we always want a data forward if it's possible, because again, the way we did it before, we didn't have to stall like we did over here. And that can be quite annoying. So whenever you can, if you see a data dependency and you see that that data dependency is coming from an R-type instruction or load immediate, then you can easily data forward. And you should absolutely data forward. The only time that we have to stall is in a case like this, where the data that we're looking for, T2, or so I'm sorry, T3, is coming from a load instruction or like a store or like something that is not an R-type. So that's when we would essentially have the stalling instead of data forwarding. Why does branch W? Oh, yeah, that's supposed to be that is supposed to be no ops. Kind of went on autopilot there. Thanks for catching that. Yeah, so branches fetch to code exec, no ops, because they end at this point, right? By the exec stage, you branch and you're done. Okay. Now we get into the branch itself. So this is one loop, right? We want to show where we're going in this case, because this is going to allow us to essentially kind of bring us to our next instruction. So we know that our branch predictor is telling us it is dynamic 2-bit weakly not taken. That means we're in this part right here, right? The weakly not taken. All I need to know right now is, okay, don't take the branch. You don't even need to say less, So because of that, right, it's telling me, okay, don't take the branch. So in my decode stage, which is where I'm going to fetch the next instruction, I fetch the next instruction, which would have been instruction 11. Well, there is no instruction 11, right? If there was, I would fetch this, but there isn't. So I can't fetch anything. It's telling me to fetch the non-branched instruction, but there is no branch instruction. So at this point, my computer thinks, okay, it's done. Now I still need to test to make sure that this is right at the end of the exec stage of the branch, right? Because right over here in this exec stage is where we're going to find out the actual comparison. Because the comparison is what tells us to branch or not. It's not the decode. All the decode is just saying is kind of biting the bullet here and saying, okay, I think we should take the branch or not take the branch. And that's where I'm going. But it could be right, it could be wrong. And whether it's right or wrong, we check our work in this exec stage. So sometimes it's good, sometimes it's bad. In this case, we know as humans, it's going to end up pretty bad because we're supposed to take the branch. So in this case, we know that we would fetch the next instruction, 11, that doesn't exist. So there's nothing that's going to be fetched over here. I'm just going to draw a line to show that nothing is going to be fetched there, right? Okay, the next cycle happens, right? There's nothing happening here, here, here. Well, now we would fetch the next instruction, which also does not exist, right? There is no 12 under here. So nothing is going to be fetched here. At this point, we do our exec, right? And we need to wait till the end of exec to figure out if we were right or wrong. So these, I guess you could say, dummy instructions will be fetched. There's nothing there, but we're going to treat it as if there was something there, right? And once we reach the end of exec, right over here, we realize, oh shoot, I was supposed to fetch something. It's that feeling when you're taking an exam and you think you're finished, okay, all done. And then the professor tells you with 5 minutes to spare, you have another side on the back that you completely forgot to answer. And this time the program realizes that. Shoot, I'm supposed to branch over here. So now I need to fetch instruction 4, and I'm going to do that 1, 2, 3. So the fetching is going to be done over here. So if you notice, you can at most fetch 2 wrong instructions, or in this case, 2 dummy instructions. So even though technically nothing is being fetched here, we're essentially wasting 2 cycles where we could have fetched something if our branch predictor had the right value. But again, all it is a predictor. It can easily be wrong. So it just sets us back a little bit. And that's okay. So in the actual like drawing of it yourself, I would just kind of show like this fetch happening over here instead. You don't really need to have these lines here skipped. You don't need to have it shown that like there's nothing really there. You could have this F over here instead, right? I just wanted to show you guys like the illustration of kind of what's going on there in the sense that it's telling you to fetch the next instruction. There is no instruction, so it's just sitting there idly for 1 cycle, sitting there idly 2 cycles. Exec's finally finished. Now it realizes, okay, I gotta fetch something. So that's what we're kind of doing over here. So now that we're actually going to fetch the right instruction because we got the right branch predictor the right branch value, right? We know that we're supposed to take the branch. I'm going to go and continue with instruction 4. Okay, now you don't have to write this out 600 times. Please don't write this out 600 times. That's just no. I think he's probably said like a story about like someone who wasted their entire class time doing that. Like, don't do that. But all you wanted to show is kind of what's going on here. So I'm going to show, all right, well, I want to go now to fetch instruction 4. So I'm going to just finish instruction 4, right? We're going to fetch and decode, right? This is a load word. At this point, there are no data dependencies because remember, 1, 2, and 3 are not part of this loop. So there's no changes to T3 and T2 at the moment. So there won't be a data dependency here. So I can just continue forward. Fetch, decode, exec, mem, and write back. Okay, and again, I just go to the next line. There's no other branch to deal with, so I continue. All right, I got myself fetch, decode. What is this? It is instruction 5. And this is adding T2 and T3 into T8. Well, we got a data dependency here now because T3 in line 5 relies on T3 in line 4, right? Same as before. Again, though, this is a load, so I cannot data forward. I'm going to have to stall. And now after stalling, now I can exec right under the W. Again, you do it under the we. Fetch, decode, we stall, exec. No memory because it's an R type, and then right back. Okay, and at this point, you're kind of good. You can just honestly go dot, dot, dot. I don't know why these dots look like 6s, but like dot, 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 dot. Like you don't have to go through the whole thing as long as it shows that you're fetching the right stuff at this point. Like we know that at this point we're going to go to 6, we're going to go to 7, to 8, to 9, to 10, etc. This is the bare minimum of what you kind of want to show here. You want to show that, hey, this is the first loop, right? Up to this point. And then these are the 2, I guess, dummy instructions, right? And this is why we set the fetch backwards a few. So that's really what you want to show. Because again, if this was saying that you started out with another branch predictor that said to take the branch, it wouldn't be like that. You would just fetch normally over here instead, because again, it tells you take the branch and you know you would fetch the correct instruction and you'd continue onward. You wouldn't have any problems. But unfortunately, that was not the case here. So when you're doing this problem, you just kind of want to show that. Now, also, especially this is going to help a little bit more when we're dealing with the CPI, right? Clock cycles per instruction. We also want to find out what's going on at the very end. So after this point, right, we know our loop was wrong. We were at weekly not taken, and this was wrong. The loop actually told us to take the branch. This means we go up one, right? The actual outcome was taken, as shown here. Now we are in the weekly taken state. So this is going to be now weekly taken. So this actually tells us something. The next time that we do this branch, we're going to take the branch. So we don't have enough room to show this. If the professor wants you to show like two loops of it, he will specify by all means. You don't have to. But if you had the room or something and you wanted to show the loop again, you could say that after instruction 10, right, we would fetch in this space over here, and this would be instruction 4, right? We would fetch instruction 4 over here, and then we would fetch instruction 5 and continue on and on and on. So we wouldn't have these blanks over here. That's what would have happened if we had the taken, and also what's going to happen on the next loop. So with that being said, right, we know that this is going to go 600 times. So we know that this itself, right, is going to keep going and going and going. And the next time that we do the loop, right, at the very end, so after it does it 600 times, the last time we do this, let's say we're in instruction 10 now, right? I'm going to do this towards the bottom just to kind of separate it a little bit, just so we can see for ourselves what's kind of going on. So this is not necessarily like happening at the same cycle as any of this, right? This is like 600 times after, right? We're going to, in instruction 10, fetch, decode, exec. This is a branch, so no ops, no ops. Now, again, we know that this is going to get data forwarded from the previous instruction and all that. We don't care about that right now. All we care about is the branch behavior. This is what's going to happen at the ends, though, right? We're going to be, the second time around, we're going to go to weekly taken. Well, we know that we're going to be taking the loop 600 more times. So this is going to give us another taken outcome and keep us at strongly taken during the remainder of the program. So just to go over again why that's the case, we started with weekly not taken. We care about the actual outcome, right? The actual outcome of the branch was taken. That brings us to weekly taken for the second time we run the program. And then the third time would bring us another taken to strongly taken. Any future takens, which would be the other 597 times, would keep us in a state of strongly taken for the rest of the program. So 600 times later, we would still be in strongly taken. So this is going to tell us, even at the last time, still take the branch. It's going to insist. Hey, we were right the other time, so continue taking the branch. So with that being said, right, this is saying, okay, so I'm going to just continue fetching. This is going to be line 4 and line 5. Fetch, decode, and fetch, right? So it's going to fetch instruction 4 and it's going to get instruction 5. And at this point, it finishes the exec stage of the original branch, right? And 2 instructions were fetched. But we know the last time the T1 is equal to 0. This is going to now be equal to 0, so it's going to tell us don't take the branch. What did we do? We took the branch. We made a mistake. So we need to get out our whiteout here and do what's called flushing the instructions out. And all this is just going to be is just X's here, right? If you've seen the X's, all this is saying is we're flushing out these instructions. So this is just going to tell us, oops, we made a mistake, and we're just going to flush out the instructions. Now, again, this is the worst case, we have to flush it out. It's not a big deal. And this branch predictor has helped us because it was dynamic, it adapted, and it switched to strongly taken eventually for the most of the program. And this helped us out a lot because we don't have to worry about this happening anymore, right? We know that each time it's going to continue running, it's going to continue to take the loop, which is great. So even if it's wrong 2 times, right, at the very beginning and at the very end, that's still pretty good. 598 out of 600, that ain't bad. So that's the whole purpose of the loops here. So if I was answering this problem, and I think this is kind of how he did it on the answer key as well, I would show the main first loop, and like where you go from there, right? So now it shows that I'm looping from instruction 10 to instruction 4. And if you have the room, I'd show the ends behavior as well. That's really all you got to do because you're not going to do all 600 times for obvious reasons. But, yeah, does this make sense? Any questions? Thumbs up? Awesome. Okay. Why lose 2 cycles? Great question. The reason we lost 2 cycles over here is because the first time we did this, our branch predictor tells us weakly not taken. Don't take the loop. So in the decode stage, right, we're supposed to fetch the next instruction. Well, if it tells us to not take the loop, then what are we going to do? Not take the loop. Go to instruction 11. There is no instruction 11. I'm not fetching anything. So I'm just sitting idle, just waiting, waiting till the exam's over, let's just say. Because in case there ends up being something, I got to just stay there until like I know for sure that I'm done with the program. So I sit idly for 1 cycle. Okay. I sit idly for another cycle. There's still nothing to fetch. Now, after this cycle, my exec is over. What happens in exec? Well, the branch is evaluated. It checks, is T1 equal to 0? If it is not equal to 0, what do? We branch. At this point, it does the calculation. It realizes, oh shoot, they're not equal. I have to do the branch. And that's why I do the branch to instruction 4, 2 cycles downward. Now, this was an incorrect branch prediction. But because it's dynamic, it switches because the outcome was actually taken. Now for the next time I'm going to go through the loop, it would be weakly taken. So we would actually not lose these 2 cycles on the second time we do the loop. And actually, at that point, it would be another taken, right? We know that we're going to continue taking the branch. This is going to bring us to strongly taken for the remainder of the program until the very end. So this is going to help us a lot. And for the remainder of the program, right, we're going to fetch in this spot over here. So we will not lose these 2 cycles anymore. We only lose them at the very beginning. So that's why we're losing those 2 cycles. Is there data forwarding between 7 and 8? No, there is actually not. So this is a good question as well that I had covered a bit before, but this is saying store T4 into the memory address represented by what's inside T2. Right, and the reason that I say, oh, it's not just T2 is because it has these address bars around it, right, the parentheses. This is literally telling me what is inside of T2. We know it's 0. Memory address 0. So it's not memory address T2. That wouldn't make any sense because T2 is a register, not a memory address. But T2 does have a value inside that can be evaluated to a memory address. That's a differentiation. So an address can't have a data dependency, right? That's honestly totally fine. So we don't have to worry about that as much. But what we do need to worry about is if this was just T2 without the parentheses. But I mean, at that point, it was updated so long ago that you don't need to worry about it. Really, you need to just worry about whatever happens in like maybe the last 2 instructions. Anything before that usually fixes itself. Beware if you have any loops If this was updating T1 in this instruction here, and then instruction 4, let's say, had a dependency on T1, you got to keep in mind how many like cycles it's been since that point. It's easy to see here. You just want to say if there's a data dependency, don't go until the we, right? It's like don't go on the roller coaster yet. So you just want to wait till that point. So in that case, right, the only data forwarding we need to keep in mind was from 3 to 4, right? This was a load immediate, which is essentially an R type, to a load word, totally fine. From 6 to 7 was a stall because it was wait, 6 to 7. Oh no, I'm sorry. It was 4 to 5. Yeah, 4 to 5 was a stall because this was a load word. I can't do it to a load word. And then we also had another data forwarding from instruction 9 to instruction 10. Again, R type to something else. So as long as it's an R type to something else, then we do data forwarding. Otherwise, it is a stall. Yeah, that's the problem with these pipeline questions. They can be a little confusing in that way, but just take it step by step. Always, like, especially in the decode stage, like, take a pause. Do not just go write out everything. You got to check decode dependencies. Are there data dependencies? Are there problems? Are there things that will cause me data hazards that will cause me to delay my program? Check for that immediately once you hit decode. Also, with branches, you need to check your branch predictor. See where you're going. It's kind of like you're stopping at a red light. For 7 and 8, the register is available in the mem cycle then. Yeah, so that's totally fine because, again, what are we doing in 7? We're storing T4 into memory address 0, right? T2 is just 0. So this is saying store T4 into memory address 0. That doesn't matter. I'm just storing a copy of T4 into some memory address. So that's fine. It may look like, oh, doesn't this go here? No, because this is memory address 0. This is register T2. At this point, they won't have the same value, right? Because we're going to update it to T4's value. But beforehand, yeah, it was the same value, so to speak, but this is the register. This is a memory address that's equal to the value inside of that register. If it confuses you at all, just break it down. What's the value of T2? 0. Put the parentheses around it. It means memory address 0. So we don't have to worry about that. Yeah, he tries to trick you up on this. I think on one of the other exams, he did something similar. So yeah. All right. Last thing about this to keep in mind is CPI. He will most certainly ask you a CPI question, and this can be kind of confusing on questions like this because it's not just like, oh, just, find out the total number of instructions and that's the amount of cycles there are, right? Single cycle processors, that's pretty much all it is, just the number of instructions. Every instruction is a cycle, but that's single cycle. This is MIPS 5-stage pipeline. These are two completely different things. So I remember on my exam, I got that mixed up, and that's something you gotta really keep in mind. If it says single cycle, just count the number of instructions. I'm pretty sure there's a question that says that here. I think it has like 3 programs, and it tells you, oh, how many cycles is it going to be on a single cycle processor? Well, you just count the instructions. But on this, it's a little bit different because we know what are cycles. They're these parts over here, right? This is cycle 1, this is cycle 2, 3, 4, 5, on and on and on and on and on, right? So this is going to run for a very long time. But we just got to kind of break it down to figure out exactly how long it will take. So, first things first, let's find how many cycles our loop is. To do this, I'm going to draw myself a little box. I start in instruction 4 on my loop, right? And I end on instruction 10. So where do I start instruction 4? Ah, right here. So right on cycle 4, I start instruction 4. This is where my loop's going to start. Where does it end? Okay, well, I keep going until I reach the end of cycle 10, right? Until the next thing loops, because we just don't want to overlap. That's really our goal here. Well, just to keep in mind, we have to keep in mind 2 different cases. The first case, which is going to be 2 extra cycles that we skipped, and the next one, which will not have those 2 cycles. So let's just focus on what we had right here. Well, we know that we won't fetch the next instruction until over here, right? Our next loop does not start until whatever this cycle is, where the fetch starts, right? This is where we fetched instruction 4. This is going to be where I'm going to end my loop box, right? I'm going to just draw a little box here, right? And within this box is where our loop is, and we count the number of cycles. That way we can find out how many cycles each loop is. So just to confirm, we start at the start of our loop, so the start of instruction 4, and we go until right before the start of the next loop. This ensures that we don't have overlapping cycles, right? And you're probably thinking, but wait, there's still some stuff here. Well, that's overlapping in the next cycle. That I don't need to worry about for this cycle because it's going to be in the next. I just want to go from everything that is only within this cycle. So let's count how many cycles this is going to be. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. That means the first time that this runs, including those 2 cycles that we kind of skip, so to speak, is going to be 10. Okay. But we know that after this point happens, we will not have these 2 unused cycles. We're going to fetch at this point instead. I'll draw this in green. Right? This is going to decrease the amount of time, the amount of cycles within each loop by 2. Because now, where does the next cycle start? Right here. This is where we would fetch the next instruction. Because why? Well, now that our branch predictor is going to be weakly taken, this tells us right from the decode stage, I want you to take the loop. This will end up being correct, right? So after this point, I don't have to worry about ever again having a bad instruction, having unused cycles, right? Until the end. Then we have to flush, but that's whatever. So that means that now I have 1, 2, 3, 4, 5, 6, 7, 8. So when the branch predictor was wrong, which was the first time, it was 10 cycles within the loop. But all the times after is only going to be 8. So you see how great this branch predictor is? Every loop we save 2 cycles. That really adds up. Okay. This is going to help us a lot because now we can figure out how many times we do our loop. So our loop is going to do a couple of different things, right? That was the first time, all the middle times, and then there's also the ending time, right? I like to think of this as the number of leftover cycles, so to speak. That's why I say it's kind of helpful to draw it out, even the end cycle over here, right? We know over here, this bottom part is where our last loop is going to happen. And we know that this was instruction 9, right? We had ourselves a fetch, a decode, an exec, whatever the rest is. That's totally fine. Okay. Now, we know that the next time that we do this loop, right? The next time we start the next loop, which, while technically it's not a real loop because we weren't supposed to, we just flush things out, it's whatever, it's going to be over here, right? This over here is where we're going to fetch the next instruction. So this is going to be the point where I draw my box, right? Over here, this is going to still be 8, right? This is going to be from before because we took our loop, we did all that. That's the previous loop, the 599th loop. We're all fine. Now we just count the leftover cycles, right? So this is going to give us 1, 2, 3, 4. Yes, there's no ops happening here. Yes, there's flushes happening here. We still count them. Okay. So we have all of our puzzle pieces now. This is great. We have the first loop, we have all the middle loops, and we have the last loops. The only other things I didn't include in the number of cycles was the very beginning. What are the parts that were never in a loop? These instructions over here. 1, 2, 3. So I have 3 here, 4 here, 10 here, and 8 times the amount of loops that we've done there. So how do I write this out? Well, I start out by saying 3 in the beginning plus 10 cycles for the first loop, right? This is only going to happen the first time because after that point, our branch predictor becomes correct. Now, 8 times, well, we had this one loop, right? We know that it's supposed to be running 600 times. One loop had 10 cycles. How many loops are left? 599. So the remaining 599 are going to have 8 cycles. And the last part is how much leftover did I have at the very end? Well, we calculated this by drawing out what the last case was. This was 4 plus 4. This is the number of cycles. The instructions is even easier, right? We know that this is the loop. This is happening 600 times. And there's how many instructions? 1, 2, 3, 4, 5, 6, 7. 600 times 7 plus how many left over? 3 in the beginning. Okay, those are my instructions. And those are my cycles. Remember, it's cycles per instruction. C divided by I. You don't have to actually solve these. Do not solve these. If you're anything like me, you will end up messing it up poorly. And actually, the professor even says, don't even do it because if you make a mistake, you'll take points off. So no need to calculate it. This is perfectly fine. All you want to show is the number of cycles divided by the number of instructions. For the instructions, just count how many lines there are. And if there's loops, multiply those lines by how many times the loop happens. Cycles are a little bit tricky, but just break it down into different pieces. I like to think of it as the loop is the meat. Like think of it as like a hamburger or something. The loop is like your meat. You have a bun at the beginning and a bun at the end. The bun at the beginning was the 3 in the beginning, and the bun at the end is any leftovers at the end. Sometimes you might not have anything at the end. Sometimes you might not have anything at the beginning. Sometimes the whole thing's a loop. Sometimes there's no loop at all. Everything's different. So you might not have something that looks like a hamburger, but whether or not you do, just break it down into pieces. So that's how we kind of answer this question. So I know that was really long, but I hope that was clear because I know this can be very confusing at times. So if you have any questions, like feel free to let me know. And also, if there's any requests for other questions to go over as well.
So Lauren, the 4 at the end, the leftover is a DENN from the, because you
Yeah,
flushed the other ones, right?
exactly. So even though there is flushing happening here, it still counts as a cycle, right? And we know that there's no ops and no ops happening here because everything has to be 5 stages. So while it looks like we could just get rid of it, it still counts. So I say anything that's from that, you could say last loop. I know this isn't technically supposed to be a loop, but from where we fetch our next instruction, because we know it's 8 cycles up to this point, these are our leftovers. 1, 2, 3, 4. So this would end up being like right over here if we were looking at it after these 8 cycles over here, right? It's after the box. Hey, any other questions? It doesn't have to be from this one. It could be another topic. General advice for the exam, really, whatever you guys want to go over. We could also take 5 minutes if you want to just kind of take it all in. Someone's confused about cores. Can you go over a superscalar question? Yeah, absolutely. Yeah, that's a great thing to go over. I don't have a superscalar question offhand. Could someone send one to me? Okay. So superscalar does have an effect on cycle time. So before we go into that, this over here was done on a single core. What is a core? A core is a single CPU. So you know how we go over the whole fetch, decode, exec, mem, write back? All this is happening on one core to one memory, right? But if you ever hear, like if you're ever computer shopping, you might hear, oh, that computer is like a 4 core or an 8 core or a 16 core. That's telling you how many CPUs you have. So think of it this way. If this is one CPU that can do all of this, imagine if you had multiple CPUs and could do more in one at one time, essentially. So instead of just running this program, I could run this program 4 times. I could separate this. I could do all different things. That's what we talk about when we have superscalar processing. Okay. Oh, perfect. There's a question right here. Okay. Yes, a core is basically a processor. That's all it means by that. Core is a CPU. So if I say that I have 4 cores, that's just telling me that I have 4 CPUs. I have 4 processors. So I could literally do, this tells me I can only do 1 fetch, 1 decode, 1 exec, 1 mem, 1 write back all at the same time. If I have 4 cores, I could do 4 fetches, 4 decodes, 4 execs, 4 mems, 4 write backs, all at the same time. Okay. And yes, his questions are usually the same blueprint. You've probably seen at this point that the problem sets, they're not identical, but they are usually a good indication of what the layout will be. Okay. So 2 of these were sent. We can definitely go over some of these. Okay. Let me do the superscalar question first, and then I'll go to the other one because I do happen to have that over here. Okay, this one's a good one to cover. Or, oh, actually, okay, I'm gonna do this one first, and then I'll do that one next. Okay. Yeah, so the part here that had the R1, this should be T1. That was an error. Whether it's T1, R1, S1, whatever, all it means with that $sign is it's a register. All right. So I'm going to do the superscalar one next. And that way we can kind of break down what's kind of going on here. And then there's one other question that involves the superscalar and also kind of covers the differences between single cycle, multiprocessing, multiprogramming, all those words and all those buzzwords that kind of get confusing after a while. So when we have over here superscalar, right? Following program is executed on a superscalar non-MIPS pipelined processor with 4 cores, with no forwarding and no branch prediction. Okay. First things first. Remember when I said, okay, we had MIPS 5 stage and we had a branch predictor and full forwarding? We have none of that now. Non-MIPS pipelining is telling me that I will not have a 5-stage pipeline. That's telling me that if I end up having a write back and a write back happening on the same core, I can't do that. I have to stall a little bit. That also means that on a good side is that if I end up having a branch that finishes in 3 cycles, I don't have to have any no ops at the end. So it has its pros and its cons. We also have no data forwarding, so that's going to be a bit of an issue because that means even if I have an R-type, I can't data forward. I'm going to have to stall. And no branch prediction. So if I don't know what the branch is going to be, then I have to fetch the next instruction regardless, and that's going to also cause a lot of inconveniences. This is going to involve a lot of stalls. So that's why superscalar is not always the greatest. But it could be made better if we had some of those parts that would have made things a little bit more smoother. So over here, right, we have loads, add, store word, add, and add, right? So the first step is to list all the data dependencies. So when I do this, I'm not going to write out a whole essay here. I'm just going to kind of say them verbally and circle where the data dependencies are. But the way I would do this is to say, for instance, instruction 2 has a T1. This relies on the T1 of instruction 1, right? Because this T2 value needs to be put into this T1 to know what memory address I'm going to here, right? Because we have these parentheses again, but it's saying the parenthesis represented by the value of T1. Well, I don't know what that value is until the end of this guy. So that's going to cause myself a problem. So for this part, I would say list all data dependencies. The T1 in line 2 relies on the T1 in line 1. That's all you need to say. I think on the answer key, he writes up this complicated chart. Don't worry about that. Just say the facts. T1 in line 2 depends on T1 in line 1. Or if it was T4, right? T4 in line 3 over here relies on T4 in line 2. Also, T1 in line 3 relies on T1 in line 1. That's still a data dependency. In line 4, this T7 relies on this T7. In line 5, T4 relies on T4 all the way back in line 2. In line 6, T7 relies on T7. Right? The T7 in line 3, not the one in line 4, because this is a memory address. So that's what you want to keep in mind. What is a memory address and what is a register? I need this value of T1 to find out what this memory address is, but this memory address will not affect this register. It's like a one-way thing. It's like a one-way door. I can go from the memory address to the register, right? That affects it. But if I go from the register to the memory address, I'm just dropping random stuff in there. That's not a problem. So that's what we want to keep in mind. So you want to just kind of write out all of that, essentially. Just say register whatever in line whatever depends on register whatever in line whatever. Keep it simple, keep it straightforward. Okay. Now calculate the CPI. So you want to kind of draw the diagram out for this, because it'll make things a little easier. So we know that we have 4 cores, right? So I know that this is going to be core 1. This is going to be core 2, core 3, core 4, right? So this is telling me that I can execute 4 instructions at the same time. Instruction 1, instruction 2, instruction 3, and instruction 4. Guess what? They can all be fetched together. Each of these cores, oops, it's supposed to be a fetch. Each of these cores is a different processor. Each processor can do exactly 1 fetch. If I have 4 processors, I could do 4 fetches. I can also do 4 decodes. You're probably saying, wow, this is so great. I could get 4 things done at the same time. I don't have to, overlap it in the sense that, my fetch would be done in this stage instead. Well, here's the problem. 4 times the productivity also means 4 times the data dependencies, especially when we don't have any hazard prediction or ways that we could fix this. So now at this point, decode dependencies. I got to decode 4 times the dependencies now. Yikes. Well, instruction 1. Instruction 1 doesn't have any data dependencies because it's the first one. So instruction 1 can just continue, right? This is a load, so fetch, decode, exec, mem, and write back. Okay, so now at this point, right, I have, shoot, what happened here? Okay, now at this point, right, I have instruction 2. Now instruction 2 is a little bit different because now we said instruction 2's T1 depends on instruction 1's T1. I need this to be completely done, so I have to stall. I have to stall until write back is completed. Now you're probably also thinking, wait, don't I wait until the we? Well, in superscalar, I can't because this is not happening on the same core. I have to wait for it to finish write backing before I can go on to the next part because it's happening on different cores. If it was happening on the same core, I'd have access to this stuff. That's why we're able to do data forwarding. That's why we're able to do all these great things. Superscalar is completely different cores, so it takes a little longer to get from one core to another. Pros and cons. Well, all right. I guess I'm going to have to exec over here then. And this is another load, so exec, mem, and write back. All right, instruction 2 is done. Now instruction 3. This relies on both instruction 1's T1 and instruction 2's T4. So that means I'm not going to be able to exec this until after the W here. So all of these guys are going to be stalls. So this over here now, I can finally exec this out. So this now is going to finish. This is a add instruction. So exec, there is no memory, but because it's not a MIPS pipeline, I am not doing 5 stages. I don't do a no-ops. So I go straight into write back. So fetch, decode, exec, write back. Now, in instruction 4, right, this is relying on T7. Well, T7 is not going to be done until over here. So my exec can't happen until after that W. So all this is going to be stall. I do not want to write out more S's. So this is all stall over here. So I'm just going to draw out a line just to show that it's going to be stall. All right, and this is going to be a store word. So we're just going to do exec, mem, no write back. No MIPS, no 5 stages needed. Okay, so at this point, right, these 4 instructions were all finished. And this was done on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is cycle 12. Okay. What about the other 2 instructions? Well, remember, each of these cores is its own processor, meaning each of these cores can do pipelining, right? Just because it's non-MIPS doesn't mean I can't do pipeline. It says pipelined regardless. It's just not MIPS. It just doesn't have 5 stages. So that means we know that core 1 has fetch, decode, exec, mem, write back. So if I have that, right, fetch, decode, exec, mem, write back. I know if I was just doing some like other, instruction, I could just fetch the next instruction down here. And I could do exec and blah, 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 blah. Continue, continue, continue. The same thing can happen here. My core 1 is going to continue over here. My core 2 is going to continue here, core 3, and core 4. So that means over here in this line, I'm going to call the next instruction. Now, we plucked all 4 of these instructions to start off with. We fetched them all at the same time. That means after this cycle, after cycle 1, when cycle 2 comes around, the 2 left over are going to be 5 and 6. 5 is going to go to C1. 6 is going to go to C2. There's nothing left. But if there was a 7 and an 8, you can imagine that goes to C3 and C4. At this point, though, there's nothing left of C3 and C4. That's okay. So over here now, I'm going to fetch in this position over here. So you can think about it. Imagine that 2, 3, and 4 are in here right now. This is just going to be a normal pipelining, right? I could do fetch. I could do decode. Now, let me see. Are there any data dependencies to keep in mind? Well, this is requiring T4, right? Because it's just putting it into register T1. So I don't have to worry about that being done. I just need T4 done. Where is T4 going to finish? It's going to finish in instruction 2. Where does instruction 2 do its write back? Over here. So we're going to have to wait until after this point. So from here to here, we're going to stall, and we can exec after the write back of instruction 2 happens. And then this is an add instruction. So fetch, decode, exec, no mem. I skip right to the write back. It's probably going to look really weird, right? It's like all unbalanced and stuff. Well, again, we're on different cores, so it's not a problem. Now, right, that's going to be 5. Now, the next part is going to be instruction 6. And instruction 6 is going to be a little different, right? Instruction 6, I fetch, but I can't decode right now because in core 2, I'm stalling. So if I had a diagram, it would look kind of like this. A stall is here and a stall is here. I can't go any further until that stall is eliminated. There was no stall in core 1. That's why I could just go as if nothing happened. Because remember, the stall, it pauses the entire pipeline. Only for that core, though. We've only been dealing with single core processors up to this point. So it looks like it's halting the entire program. But in reality, it's only halting the part of that one core. So that's why core 1 didn't have to stall because there were no stalls. Right, it just had to stall because it was missing data. This guy, though, he needs to stall until core 2 is done. So I can't decode until I finish my stall here. I can't decode till here. Now that I'm in decode, I can actually see even if I have data dependencies. So that stall was just because core 2 had a data dependency a while back and was stalling the entire chain. This has nothing to do with the fact that right now core 2 might also have a data dependency for line 6. Line 6 requires T7. Well, where was T7 updated? Again, 4 was the memory address represented by T7. But 3, the actual value of T7 was updated. So where was that done? It was done right here. So that means I have to stall again up to this point. So I'm going to exec over here. This looks crazy. 1, 2, 3 stalls, 1, 2, 3, 4 stalls just to get me from fetch to exec. Yikes. But that's the problem with these superscalar processors. Now I could finally finish. I got my data. I'm all good. This is an add instruction. I could finally do my write back. And at this point, I would be done here. So this is taking exactly 12 cycles for everything. So this is our superscalar. And clock cycle per instruction, right? So how many instructions are there? 6. How many cycles are there? 12. 12 divided by 6 is your CPI. And that's it. Questions? Okay, why instruction 5 do like a pipeline and do not need to wait until instruction 1 finished all stages? 5 and 1 are being done on the same core. Each of these cores, right, can do pipelining. Core 1 does pipelining with instructions 1 and 5. Core 2 does it with 2 and 6. This is just saying I'm fetching 4 instructions and putting them on each core. 1, 2, 3, 4. Think of it like factories. 4 factories are producing it at the same time. And you're getting those 4 things done at the same time. When one factory is done, you feed it another instruction. So because it tells me that this is a pipeline, I can do that. Each core can have a pipeline. Now, if this did not say pipeline, I couldn't do that. Then I'd have to wait till the end of this instruction in order to fetch the next one. But because it says pipelined, I can do that, right? It just says non-MIPS. All that means is I just can't have 5 stages. So that would be the issue there. So with these problems, just keep in mind where each instruction is going to, what core it's going to. Keep in mind if there's any stalls happening. And remember, 4 times the processing also means 4 times the data dependencies. There could be a lot of problems there. So be very careful with that. Okay. Any other questions about this one? If not, there was one other question I saw. Yeah, of course, no problem. Happy to help. Okay, if not, there was one other problem that I wanted to go over that I saw, which was sent. And this one kind of goes over the difference between multi-programming and multi-processing. You have a question in 6? Wait, also in the first question, or in 6, how come the decode it stalled? Was it in use by 5? So that was actually not the case, right? Because this is core 1, this is core 2, right? You can literally think of it as, let me actually highlight this, right? This is core 1, this is core 1. This is core 2, this is core 2. And core 3 and core 4 don't really matter at this point because they're not being used again. But right here, you see, core 1 is in pipeline with core 1. Core 2 is in pipeline with core 2. If we look at the green, what do we have over here? This is a stall happening, meaning anything in the pipeline of core 2 is going to be stalled. So you could think of it as literally there's a stall here, a stall here, a stall here, down only for that core. So core 1 is not affected by that same stall. Core 3 is not affected by that same stall. Core 4 is not affected by that same stall. They're stalling for a completely different data dependency. That's why it looks like the pipeline should be stalled in the whole cycle should be stalled, but it's only per core. You only stall the whole pipeline per core because that's really what pipeline is. Pipeline is per core. It's like each core is its own Chipotle restaurant, and you can do pipelining there, right? I think he's gone over the Subway/Chipotle example. Think of each core as its own restaurant. So if one core stalls, one restaurant stalls, you could still get your order from another restaurant. If you have different colored pens, might help to draw it out like that on the exam. Don't think he would have a problem with that. Just like honestly write it out, like core 1, core 2, core 3, core 4. That way you know kind of what's going on. Okay. There's no more questions on this one. I have one other one that I had wanted to go over. And then at that point, I think we might have covered pretty much everything else. Because a lot of it really comes down to pipelining. Like, if you understood that first example we did, which was a little bit trickier, like that really combined everything. It had data forwarding, it had branch prediction, and the hardest branch prediction, mind you. It had CPI, it had loops, it had pretty much everything that you can think of. So if that one made sense to you, like you're good. Like just keep going over the examples. Try to keep doing them yourself. You gotta really practice this stuff. So as long as you do that, you should be honestly good. So I did want to just cover this last example because this one is a little different. I had brought up kind of the difference between single cycle and like pipelining before, but let's just go over it a little bit again. Single cycle is literally what it's saying. Each instruction is a single cycle. So this is one cycle. This is another cycle. This is a third cycle. This is a fourth cycle. So we're asked to calculate the total number of clock cycles for the above executables on a single cycle multi-programming single processor system. Wow, there's a lot of stuff going on here. But let's just focus on the single cycle part, right? Single cycle is saying for program 1, there's 1, 2, 3, 4. 4 cycles. 4 instructions, 4 cycles. We know 4 divided by 4 is 1. Single cycles always have a CPI of 1. But this is also saying a multi-programming single processor system. Okay. Well, here's the thing. If you have a single processor, this is your CPU. Your CPU can only fetch one thing, to code one thing, exec one thing, mem one thing, write back one thing. But this is said it's a single cycle, meaning I can't do fetch and decode and exec and mem and write back all at the same time. If that's the case, I'm going to have to do one instruction at a time. So that means I do instruction 1, 2, 3, 4. Then I go to program 2. 1, 2, 3, 4, 5, 6, 7, 8. Here. And there's a loop here, but we'll get back to that in a second. 1, 2, 3, 4, 5. And again, there's a loop here. We'll get back to that in a second. So that's literally saying these 4 instructions, sorry, plus these 8 instructions, plus these 5 instructions, one after the other. So that's something to keep in mind when we have a single cycle, single processor system. I don't care that it's multi-programming. If you have one CPU, you can't delegate these to other processors. There are no other processors. Similarly, if it was the other way around, single programming, or uniprogramming it's called, multiple processors, even if I have multiple processors but I don't have the programming ability, I can't do anything with it. I can't split them up. The only way I can do multi-programming is if I have multiprocessing, multiple CPUs, that's all that means, and a system, an OS, operating system, that can handle actually doing the delegation. So that's the main difference between these two examples. So the first one, right? I said all we're doing is just counting up the cycles. That's really all we're going to do because it's 4 plus the 8 plus the 5. Now, we do have loops here. So we got to figure this out because it's not just going to be 8 cycles. It's not just going to be 5 cycles. It's going to be more than that because if the loop happens, it's going to happen a bunch of times. Well, we know we have load immediate, T7 is 0, store word, bunch of other stuff. All I really care about is this BLT. No, it's not a bacon lettuce tomato sandwich. I wish it was. But this is branch on less than. This is saying I branch to label X if T7 is less than T4. What is T7? T7, we're going to add 1 to it. It starts out at 0. So 0 becomes 1. T4, on the other hand, takes on the value. Let's see. We're loading in memory address 12. What does memory address 12 have in it? Right? Because we care about the value inside of those parentheses. We have to open up the parentheses. Well, it says assume each data memory location contains an initial value of 10. So T4 has a value of 10. So every time I'm doing this comparison, I'm quite literally comparing the value of T7 to the value of 10. Each time that this register is less than 10, I do my loop. So if 1 is less than 10, I do my loop. Okay. If 2 is less than 10, I do my loop. 3, 4, keep adding 1 to it. How many times is this going to run? 10 times, right? It's going from 0 to 10. So I know that this part, the loop, from label X to the BLT, is going to run 10 times. Okay, how many instructions are in this loop? 1, 2, 3, 4. 4 times 10. 4 instructions per loop, 10 loops. How many leftovers do we have? This is a hamburger bun. That's all it is. There's 2 at the beginning and 2 at the end. Plus 4. 44. Whenever you're finding cycles, just think of the hamburger example. The loop is your meat. How many times you're looping is like the stack of patties. And then you have your bun on either side. Great. Now we just need to find the number of loops on program 3. Well, program 3 is saying, again, I don't really care about the other stuff, branch on greater than if T7 is greater than 9. T7 starts out as 1 and it does not change throughout the whole program, right? This is saying to add T7 and T4 and store it in T5, but T7 never changes. Therefore, 1 is not greater than 9. We never do the branch. This is always just going to be 5. So now that we know this program is 4, this program is 44, and this one is 5. It's a single cycle, meaning each instruction must happen one after the other. I cannot pipeline them. I can't layer them. So that means instruction 1 happens, instruction 2 happens, 3, 4, 5, etc. If each of these instructions is one cycle, I can just add up the total number of cycles to find what it would be in a single cycle processor. So super easy, right? Literally just 4 plus 44 plus 5. If you have a single cycle, single processor system, or really anything that is not multi-programming, multi-processing, it's just adding the cycles. So that part would be really easy, right? Add that up. You don't even need to, I'm pretty sure that would be 53. But just don't even worry about finding the actual value. Now, where it gets different is if we have multi-processing and multi-programming. So again, everything will be single cycle, just like this, adding up the cycles, unless it is multi-processing, multi-programming. Just try to drill that into your brain. If it's multi-programming and single processor, no good. If it's unit programming, all right? And it's multiprocessing, still no good. If it's single processing and unit programming, even worse. It's going to be the same thing if it's unless it's multiprocessing and multiprogramming. This is the dream team you can think of. You have multiple CPUs, multiprocessing. You can process multiple things. You have multiple CPUs. That's like the superscalar example we went over. And multiprogramming. You have an operating system that knows what to do with these cores, right? If you have 4 Chipotle restaurants and you have a manager that doesn't know what they're doing, they can't manage all 4 of those restaurants. You need a manager that knows how to manage 4 restaurants at one time. Think of it that way. So, in this case, this allows us to actually layer things together. I know I have 2 processors. Let's think this is processor 1, and this is processor 2. Processor 1 can handle one of these programs, and processor 2 can handle one of these programs. Now, best case, imagine that, well, actually, let's go over the worst case first. The worst case is exactly what we've done. It can't get worse than doing one after the other after the other. If we, for whatever reason, I don't know why we would do this, but only want to use the first processor and store everything on that first one, right? I could do the 4 from program 1 plus the 44 on program 2 plus the 5 on program 3 and still get 53 cycles. Because what is this single processor saying? One processor, one after the other. I could still do that here. I don't know why you would do that, but you can just say, I'm not using my single processor. That's your worst case. What I can also do, though, is I can layer it a little bit. If I said 44 cycles, program 2 will be on P1. During those 44 cycles, right, I can do program 1 and program 3. Program 2 is only 4, and program 3 is only 5. This will finish in 9 cycles total. It happens simultaneously with program 1. Because of that, right, we know that the whole thing is only going to take up 44 cycles. Because the other 2, the remaining 9, will happen at the same time as those 44 are happening. So that we don't need to worry about. So this is what it allows us to do, right? If we go back to that superscalar example, that's literally what we had here. If we did not have multiple CPUs, think of all of these guys one after the other, after the other, after the other. It would be so much longer. But that's not what's going on here. We have 2 CPUs here, just like we had 4 CPUs here, 4 processors. We could process 4 things at the same time. Here we could process 2 things. I could let P1 go for all the cycles it needs while I have P2 doing something. I mean, think of it as if you're using your own computer, right? Your computer has a lot of cores to it. You can listen to music and surf the internet and type a document and do a whole bunch of other stuff all at the same time. That's what your cores allow you to do. Each core can handle one part of a process at a time. So that's what we mean by the worst and the best, right? Worst is, again, if we just have everything happening one after the other, literally same thing that we have here. Best is the most optimal way to layer things so that it happens at the least amount of time. Think of like splitting up a project with your friends, kind of what you're doing here. So that is the end of that problem. Any questions about this or anything else? Problem 2 of the exam. Which one is that? Is that the branch predictor one? Like the one that gives you the... Yeah, we could go over this quick. This one's a quick one. This one over here, right? Awesome. Okay, let's do that. And then someone said they have a question with the first one on this one. Okay. Let me actually do this one first, just because this is pretty much identical to what we did on the last one. And then we'll go to the branch predictor one, and then at that point, call it a day. Okay. So this is the exact same thing that we had before, right? Calculate the number of clock cycles for the following programs. The programs are executed on a non-pipelined, multi-programming system, no multi-processing. Okay, we're missing something here. Multi-programming, we have a manager that can, manage a bunch of restaurants, but we don't have the restaurants for him to manage. How are we going to do anything? This is just going to be single cycle. Count all of the instructions. That's literally it. Next, we have over here a multi-processing, but no multi-programming. We have multiple restaurants. We have no idea how to manage them all. Same thing, count the instructions. And then provide the best and worst case number of clock cycles if the programs are executed on a non-pipeline, multi-processing, and multi-programming system. This is the good one. This allows us to layer things. So, okay, there's no branches here. We could just count these up then. 1, 2, 3, 4, 5. So this is 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5. Okay, cool. All right, for the first two, literally 5 plus 6 plus 6 plus 5. That's it. That's literally what it would be for A and B. For C, it's going to be a little different because we want to do the best and worst case ways of doing this on a non-pipelined multi-processing and multi-programming system. Interesting. We're not provided the number of cores. Or am I going crazy? Okay, well, he didn't provide us the number of cores. So we're going to have to assume on this one. First things first, worst case is just the same. Yeah, we could just assume 4. If something like this happens, I don't think he accepts questions during the exam. Just usually like assume something, you know. He should tell you not to make assumptions or what you can assume if there are any problems here, but usually you'd have to kind of, but that's fine. Worst case is literally just what we did before. Everything happens at the same time. Now, if there's 4 cores, let's just think core 1, core 2, core 3, core 4, right? Each of these cores can take a program. This takes program 1, program 2, program 2, program 3, program 4. Which one is going to take the longest? Well, program 2 and 3 both have 6 instructions. Therefore, this will take the longest. It will take a minimum of 6 instructions to make it through everything if they're happening simultaneously. So if that was the case for 4, we could say that. Now, let's just play around with it because, well, that one was pretty simple. What if we only had 2 processors? I can layer this a couple of different ways, right? I could do a program with 6, a program with 5, a program with 6, a program with 5, right? This means 11 on the top and 11 on the bottom. These are even. I could also do something like 5 and 5 on the top and 6 and 6 on the bottom, right? The top being processor 1, the bottom being processor 2. This means 10, but 12. So even though the top has less, the bottom is what's going to take over because the largest time is going to be the total finishing time. I want to find a way to split it as even as possible. So if this is the case, the top way is going to be our most optimal way of doing that. Put one instance of the 6, one instance of the 5, one instance of the 6, one instance of the 5. right? You just want to find the best way to split things evenly. So that's how I would do something like that. And again, you can play around with this with all different ways of doing that. As long as you have good reasoning, it should be fine. So that's kind of how we're doing that. And he should give you the number of cores. You're not supposed to really know how to do that if they don't give you that. I'm going to assume it was probably 4, or it could have been 2, whatever it was. All right, the second one is a little different, right? Calculate the number of clock cycles for the following scenarios. The executable is executed in parallel on 4 single cycle processors. Okay, so this is literally what we did in superscalar, right? So we know we have 1, 2, 3, 4, 5. If this is done on 4 single cycle processors, right? There's 5 instructions total, meaning 1, 2, 3, 4. One of these is going to have to get 2 lines of code instead of 1. So we know that neither of these are going to be on MIPS, right? This is just single cycle. So each line of code is going to be 1 cycle. On the solution, the best case is 6 cycles. Yeah. If it's 4, yes, the best would be 6. If it was 2, then it would be best is 11. It's whatever the largest processor risk would be. So on this one, right? We know that this is going to be single cycle, so each of these takes 1 cycle. Well, if each of these has 1, 1, 1, 1, one of them needs to get a second one because there's 5. So one of these guys is going to take 2 cycles instead of 1 cycle. The largest cycle will be the total time that it'll take. So that means one of them will have 2 cycles, so it will take minimum 2 cycles to get this done. On the other hand, if we had MIPS, right, 4 5-stage MIP pipeline processors, right, we can draw out the diagram for that, right? So, I don't want to draw out that whole thing right now, but just remember you have like fetch, decode, exec, mem, write back, etc., right? So this is kind of going to let us, like, not have to worry about that as much in a sense. And because of that, right, that's going to be kind of what we're doing on the superscalar side, right? So if we had core 1, core 2, core 3, core 4, just like the last one, right? We would do our fetch. Okay, core 1, we would do our fetch, our decode, exec, mem, write back, right? Core 2 will fetch as well, continue whatever it needs to do, fetch, continue whatever it needs to do, fetch, continue whatever it needs to do. Now, core 1, or really any of the cores, would be free at this point. I'm going to just say core 1 because if it starts first, it probably is going to finish first. Right? Because they're all going to be 5-stage, so it actually really doesn't matter because they're all going to take the same number of time. So now, right, ignoring all these other cores, think of core 1 as its own pipeline. If I fetched here and decoded here, I could fetch again on that same core over here, and then decode, etc. So we're going to take instruction 1, instruction 2, instruction 3, instruction 4. These 4 are going to happen at the same time, and then 5 is going to happen 1 cycle later. So if each of these takes 5 cycles, right, this guy's going to kind of be a little bit behind. He's going to take 1 extra cycle, so 6 cycles. Now, this is not including data dependencies and everything. So just bear in mind when you actually do the problem and everything, if there's data dependencies, there's no stalling. There's like if there's stalling, if there's other things that might delay it. But essentially, we know that instruction 5 is going to be 1 cycle behind. So that's the main thing. And then the last part is one instance of the executed on a superscalar vector processor with 4 instruction registers, 4 memory data registers, and 4 memory address registers, and 4 ALUs. Okay. So that's quite literally the superscalar that we did before. Yeah, that's pretty much the same thing here. The only thing that we don't have is we don't have 5-stage, right? Because it's not the same as before. So, unlike before, in case there was like a branch or something, or an R type that would be fetch to code exec write back, now we have the no ops included. So that's the only difference between this and this. MIPS tells you that you have no ops, everything has to be 5 cycles. And then the other part, if it's superscalar vector and it doesn't tell you MIPS, then you don't need to include no ops. So you could have a R type that goes fetch decode exec, skip mem right into write back. So that's what we're doing here. And then going back to this one, right? This is similar to the one that we did here, right, where we went back and forth between the different Right. Okay, thank you. But can you explain why you group 2 processors together for the first question when there is 4 processors? 4 processors, there's 5 instructions. 1, 2, 3, 4, 5. One instruction is going to need to have one, you're gonna have 2 one processor needs to take 2 instructions. Think of the pigeonhole principle, right? Wait for this one, the top one over here, why I grouped 2 together. Oh, this was just an example. This is with 4 processors. This is with 2. We didn't know what he gave. I just did it 2 different ways. So yeah, I mean, I don't know what he's gonna give, but now you know how to do it 2 different ways. Okay. And then this one, just to quickly go over what exactly is going on here, right? Dynamic 1-bit taken, right? We start out with taken, and this is saying our outcome is actually not taken. So dynamic 1-bit just switches between it if it's wrong. So I have originally taken. My outcome was not taken. I switched to not taken. Now I'm starting out at not taken. What is my outcome? Taken. Let me just cross these off as I go along. Okay, now I'm wrong. I switch to taken. I start out at taken. My outcome is not taken. I'm wrong. I go to not taken. I'm not taken. Now I have not taken. I'm correct. I stay at not taken. I have not taken. My actual value is taken. I switch to taken. I'm at taken. My actual value is taken. I stay as taken, and continue on and on and on through that. That's how dynamic 1-bit works. Dynamic 2-bit, on the other hand, is like that automaton that we think of before, right? Strongly taken, weakly taken, weakly not taken, strongly not taken. If you have a taken outcome, it brings you up. If you have a not taken value, it brings you down. So we're starting out at weakly not taken. What is our outcome? Not taken. That brings us down the chart to strongly not taken. Now I'm at strongly not taken, but I hit a taken as an outcome. That brings me up 1. I'm back to weakly not taken. I'm at weakly not taken, and I hit a not taken. That brings me down the chart. Strongly not taken. I'm in strongly not taken. I hit a not taken. I stay at not taken, right? I can't go any further down the chart. This just continues looping if I hit any more not takens, just like this continues looping up if I hit any more takens at strongly taken. Okay, strongly not taken, not taken, stay at strongly taken. Sorry, strongly not taken. And continue onward, right? Strongly not taken. I hit a taken. I go up the ladder for weakly not taken. I'm at weakly not taken, and I hit another taken. I go up the ladder, now I'm weakly taken. I'm just going to do one more. There was a third true here. Taken here. I'm at weakly taken. I hit another taken. I go up to strongly taken. And continue on and on and on and on. The key to remember is, what is your actual value? Am I right or am I wrong? Do I go up the ladder or down the ladder? That was like the example that we did at the very beginning. This one over here, right? We started out at weakly not taken. That was incorrect, right? And after the first iteration, we went to weakly taken, right? The actual value, it told us we should have taken that branch, so it brings us up the ladder. And then again, we were taken, right? Because we keep taking this branch, and that would bring us up the ladder again to strongly taken. So that's how we do branch predictors. And the accuracy part, it's how many times that you were correct. For instance, if any time I have a not change here, so like this is a not change, this is a not change, you count those. So if this was 2 out of however many there are, 1, 2, 3, 4, 5, 6, 7 that we did, 2 out of 7. That's obviously not the answer. There was way more than that, but you get the picture. And in this case, right, if I stay at not taken, then I'm good. So weakly not taken and strongly not taken is fine. Strongly not taken, weakly not taken. This brings me down 1, right? So this was not matching with taken. Weakly not taken, my outcome was not taken. This one is good. Strongly not taken, that's good. Strongly not taken actually was taken, no. Weakly not taken actually was taken, no. Okay, so this would have been 3 out of 7. Again, only in this case, this is not the actual question, like, because we didn't do the rest of these, but at this point, now you kind of get how to do that. He might ask a question like this. Draw out the automaton, the state diagram. Sorry, I kind of have 320 on the brain. Draw out like this little state diagram, little ladder, whatever you want to call it. Go up the scale for taken, down the scale for not taken. If you do that, then you should be good. So what I recommend you to do to study for this test, do as many of these problems as you can. This one especially, do ones that look like this because this kind of has everything involved in it. So that's the end of that. Any last minute questions before we end the session? All good. All right. Well, this will be posted onto the on the Learning Commons website. Please fill out the review wait, was it the feedback form? Sorry. Please fill out the feedback form for this review, which is currently in the chat. We appreciate your feedback a lot. So just fill that out and you're welcome to leave, and best of luck with your exam. So this will be posted on the Learning Commons website. I'll also be sure to ping in the Discord when that happens. So thank you all, and don't forget, please fill out the form.
Bye-bye.
Bye.